is a mass. If we put m is equal to half, and then it becomes half r square theta dot. So since angular moment is a constant, so half r square theta dot can be written as a constant. But if you check, this half r square theta dot is nothing but the areal velocity, because if the radius vector r rotates through an angle d theta r vector in time dt, then the area swept out is equal to half r into r d theta. Area of the triangle half r this side into r d theta, which is basically half r square d theta. If we take its time variation dA by dt, then r is fixed, so only taken derivative d theta by dt, so it becomes half r square d theta by dt, that means half r square theta dot. But we already found that half r square theta dot is a constant, so we can say this quantity dA by dt is a constant area varying per unit time, which is nothing but areal velocity. So areal velocity is a constant, which implies radius vector sweeps out equal area in equal time interval, which is Kepler's second law. Okay. Then Kepler's third law, we know that the t square time period square proportional to aq. Okay, so now derive that. For that we assume that planets are revolving around the sun in an elliptic orbit, and for an elliptic orbit the semi-major axis is one half of the sum of two apsidal distances r1 and r2. If we see, this is your ellipse, and r1 r2 means position coordinate of two focus points, or 2 for C. If this is R1 and second one R2, then what will this point A? A is R1 plus R2 by 2. By definition, the radial velocity is 0 at these points. Okay, because radial velocity is 0 at the turning points, where we say we already saw in the previous classes that at turning point radial velocity r dot is 0. So this turn, it is a turning point, this is a turning point r dot is 0. So the expression of energy conservation equation becomes energy conservation is kinetic energy plus potential energy, half m r dot square plus j square by 2 m square plus vr. After converting theta component, we got this j square by 2 m square. If r dot is equal to 0, then this term vanishes, so total energy becomes j square by 2 m square plus vr. Again, for Kepler problem, we have potential energy equal to minus k by r. So energy becomes j square by 2 m square minus k by r. Okay. When we make it 0, then we found E minus j square is 0, or which actually give this expression 1. Is not it? Hello? Hello? Okay.
Yes, sir. Yes, sir.
Okay. So actually root of this equation gives you two radius, because r square, so there are two roots. It's a quadratic equation. It has two roots. And roots of these two roots are basically two radius, r1 or r2. Okay. So it is quadratic equation. How you get the solution? Ax square plus bx plus c. So in place of a, here 1, b k by e. Isn't it? This is your b. Then c, the root where? Hello? For quadratic equation, what are the roots? Ax square plus bx plus c is equal to 0. The root will be x is equal to minus b
plus minus b square
Minus
minus
b
4ac.
plus and minus root over of b square minus 4ac by 2.
Okay. So here a is equal to 1, b is equal to k by e, and c is equal to minus j square by 2me. Okay. We can calculate the root. If you add these two roots, then what will the value?
minus b by a.
minus b by a. Okay. So root, if we add these two roots, we get minus b by a. Okay. So now we know that semi-major axis is R1 plus R2 by 2. Okay, what we have already discussed. If this was in R1 and this is R2 second point, then R1 plus R2 by 2 is equal to midpoint, which semi-major axis. So R1 plus R2 by 2. But R1 plus R2 is nothing but sum of two roots minus b by a. B is equal to k by e. A is equal to 1. So minus b by a is equal to minus k by e. So here R1 plus R2 by 2 to minus k by e by 2 to minus k by 2e. Are you getting my point?
Yes, sir.
Okay. So this one then. So here tightly rearranging, I can say E is equal to minus k by 2a. But we know that eccentricity from Kepler's first law. We have a formula eccentricity square root of 1 plus 2e j square by mk square. Putting minus k by 2a in place of E, we get eccentricity is equal to nothing but square root of 1 minus j square by mk. Yeah. So again from the conservation of angular momentum or the real velocity is constant second law, we know that dA by dt is equal to half r square theta dot. Theta dot is nothing but j by mr square. Putting that, we found j by dA by dt is equal to j by 2m. So the total area is j by integration of j by 2m into dt or dA by dt into dt. This integration gives you area dA by dt into dt. It's integration over complete time period 0 to tau. dA by dt into dt cancel. dA integration means a 0 to tau, but dA by dt is j by 2m into dt. So if integrate it, you find t, putting the limit j by 2m tau. But if A and B are semi-major axis and semi-minor axis respectively, then the area of a ellipse is equal to pi AB. It must be equal to pi AB. So j by 2m tau is equal to pi AB. So tau is equal to 2 by mj pi AB. Time period. Again from the formula of eccentricity of a ellipse, we know that B is equal to A into square root of 1 minus E square, where E value is 1 minus j square of mk. We already calculated here E value in equation 5 eccentricity. So putting this, we found B is equal to nothing but A into square root of j square by mk. So A root take cancel, so A to the half j square by mk root over. So tau is equal to how much? Putting the value of A and B, we found 2 by m pi A B. In place of B, put this. So it becomes A to the A into a half, A to the 3 by 2. So final expression this, that is tau square proportional to AQ or tau proportional to A to the power 3 by 2. This is Kepler's third law. Clear?
Yes, sir.
The square of time period of a planet is proportional to the cube of its semi-major axis. If we consider the exact motion of the planets around the sun, it is a two-body problem because one planet is moving around the sun. We can also use the reduced mass concept, that reduced mass is equal to m by, where small mass of the planet, capital in the mass of the sun. Okay. Again, from we know the attractive gravitational force between planet and sun is equal to minus g mm by r square. Actual sign is minus g because minus for attractive. Okay. If central force is attractive, sign will be negative. But in plus 2 books, it was written positive, only magnitude they are considering mod. They are cutting the modulus only. But actual there is a minus sign. This is attractive force, this should be minus sign. Minus g mm by r square. So if you compare with k by r square or force minus k by r square, so k will obviously j small m into capital M. Because here there is the k, we put that value k here. J m by m. So putting in that place, the equation of time period becomes 2 pi a 3 by 2 m by k. K means gmm here. Okay. But if you use the reduced mass, but this m is actually reduced mass. In place of a mass of the planet, if we consider two body, that m represents reduced mass. This expression mm by m plus m. So here in numerator you put m by m plus m, and denominator you put gmm. So actually cancel. So we found only 1 by g m plus m. Since mass of the sun is much greater than mass of planets, so it can be finally reduces, it can be neglected small m, so root over of gm. This is the final formula and for calculation of time period of planets. Okay. So using this formula, time period of planets can be calculated. Okay. Hello.
Yes, sir.
Okay. This is a proof of third law. Then we go for Laplace-Runge length vector. Actually, this question comes in your examination about Laplace-Runge length vector. This is another constant of motion for central force motion. Okay. Like angular momentum, energy, aerial velocity, Laplace-Runge length vector is a constant quantity for central force motion. How we derive it? Actually, for this, we come from the Newton's second law that force is equal to rate of change of momentum. So P dot means dP by rate of change of momentum is equal to force. Force means if I consider its magnitude Fr, then direction r cap. In place of r cap, here I write r by r vector. Okay, there is no problem. Because you know r cap is equal to r vector by r. So now take cross product with this P dot j. It will be Fr r cap dot j, but j is equal to r cross P. Okay, take the cross again. P is equal to mv m r dot. Okay, so this will be Fr r by r cap. Remember, taking all scalar part outside, that Fr r here m, we got m Fr by r and bracketed r cross r dot. Okay, A cross B cross C. So there is a general formula for A cross B cross C equal to B A dot C minus C A dot B. Is not it? Hello? There is a formula A cross B cross C. In your vector identity, I think only know from mathematical physics. There is basic. What is the formula A cross B cross C? Any idea?
B into C dot A minus.
Vector triple product actually commonly called back minus cap. B A dot C, or it is sometimes written B vector, because a vector triple product is a vector, cross product is a vector, B cross C, again it is multiplied with another vector cross product, so it is a vector. So vector part actually B is formula is B A dot C minus C A dot B. B A dot C minus C A dot B. B A dot C minus C A dot B. Okay? Hello?
Yes, sir.
This is the formula for vector triple product. Okay, so here in our case, A is equal to R, B is equal to R vector, C is equal to R dot. Okay, so put here B, R, A, R, C, R dot. Okay, first on B, A dot C, minus C, A dot B, C is R dot. Again, A dot B means R dot R. R dot R is equal to same vector R square. Okay, isn't it? Hello?
Yes, sir. Yes,
Okay.
sir.
But R dot is equal to, I can write it, R dot means dr by dt. So R dot dr by dt. Since dot product is commutative, A dot B is equal to B dot A. So we can write it is R dot dr by dt same as dr by dt dot R. Okay. So we have R dot dr by dt or vector. I am not using the vector. R dot, sorry, dot, it will be R dot dr by dt. It is same as if you write first dr by dt then R. It
Yes,
is
sir.
okay. So now add these two. This means 2 dr by dt dot R. So I write here. So it is actually R dot dr by dt. Since it is same as dr by dt dot R, I here write d by dt R dot R. A dot db by dt plus b dot da by dt is nothing but d by dt dot b. Okay, a simple vector algebra. So
Half, sir.
basic. So r dot r means r square. I can write like this: half d by dt r square. If we take derivative, now it comes to scalar. 2 cancel. 2r into r dot, chain rule. dr square by dr into dr by dt. dr square by dr is equal to 2r. 2 half cancel, only r into r dot. So this value is nothing but r into r dot. I put here r into r dot. Now I multiply 1 r square and divide r square. So it will be 1 r cancel. So r dot r vector by r square, r dot by r. Basically this term can be written like this, which is derivative of a term. Because derivative a by b is equal to b derivative of a minus a derivative of b by b square. Okay. So this term is derivative of r vector by r. Why I write this? Because these are m. Okay. Again, here m is a constant. I want to put here some constant because we know for Kepler's problem f of r is equal to minus k by r square. So f of r into r square is nothing but minus k. So multiplying this, I find this point mk d by dt r by r. For m is a constant, k is a constant. So I can take inside the derivative. Since they are constant, they are not affected by derivative. So I found this derivative of p cross j is equal to derivative of mkr by r. Taking one side and taking derivative as common, the derivative of p cross j minus mk by r is a 0, which means this bracketed term is a constant. And this bracketed term is known as Laplace-Runge length vector, which is denoted by a. Okay? Hello?
Yes, sir.
This is Laplace-Runge length vector. Since j is perpendicular to p cross j, the term p cross j, p cross j is perpendicular to j, and r is perpendicular. This term r is perpendicular to j because j is equal to r cross p. from rule of cross product, J is perpendicular to both R and P. Then we can say A is perpendicular to J. So A dot J is equal to 0. Because this term is perpendicular to J, this term is perpendicular to J. So what it implies? J is perpendicular to J. A dot J is equal to 0. From this I can, or we can derive the Kepler's law. So why it is important? Because using Lorentz vector, we can derive the Kepler's law. A dot J is 0. So A must be some fixed vector in the plane of the orbit. Because A is perpendicular to J. We already know that central force motion J is a constant. And so central force motion occurs in a plane. Now A dot R is equal to A R cos theta formula. But A is putting the value of A as Laplace Lorentz vector P cross J minus M K R by R dot R. So AR cos theta is equal to R dot P cross A dot B is equal to B dot A minus here C M K R dot R vector is only R square by R cancel 1 R to M K R. But R dot A dot B cross C, this formula A dot B cross C is same as B dot C cross A is same as C dot B cross A. A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. So it is general identity, vector identity. So using that A dot B cross C, I found A is R, B is P, J is C. C cross C dot A cross B, C dot A cross B, but R cross B is J, so it finally J square. Simple use of vector algebra. Okay. So finally we found AR cos theta is equal to J square minus MKR. Or simplifying this, J square by R is equal to A cos theta plus MK. Or 1 by R is equal to A cos theta plus MK by J square. Okay. So now taking MK by J square common, we found 1 by R is equal to MK by J square 1 plus MK cos theta. But this type of formula we found in the Kepler's first law for the equation of orbit. So Laplace length vector is another way to deriving the orbit equation of the Kepler's problem or derivation of Kepler's first law. In Kepler's problem, we have a formula 1 by R is equal to MK by J square 1 plus epsilon or E cos theta minus theta prime. Now setting theta prime 0, we can write epsilon cos theta. So what A by MK is equal to E. So A is MKE. Magnitude of A can be written as MKE. Again, E is equal to this formula. So putting this, you can say A is equal to this, or A square is this quantity. So for Kepler's problem, we have two vector constants from J and A of the motion J, A and scalar E. Okay. These are constant of motions. Since A is a vector, a constant means all three components are constant. So there must be three constants, Ax, Ay, Az. Again, J is a vector, is a three constant, Jx, Jy, Jz, and E is a constant. So total 7 quantities are conserved here. Okay. In general, orbits for central force motion are not closed, but if the orbits are degenerated, there exists additional conserved quantity is an algebraic function of R and P, such as Laplace Lorentz vector. Thus there exists. Okay. So this is the importance of Laplace Lorentz vector. You can derive Kepler's problem directly from this by using this. Okay?
Yes, sir.
Okay. Another important thing is our small oscillation. We did and we go. It is very important. Small oscillation. Small means amplitude of oscillation is very small. When amplitude of oscillation is very small, we call it small oscillation. In general oscillation, for suppose a simple pendulum, we have many laws on the time period, calculation time period, 2 pi L by 0 root over everything. That is only valid when uh, amplitude of oscillation is very small, deviation is very small. You also do it in practical, I think in class 3, and calculation of time period of simple pendulum. At that time, you take the deviation very small, amplitude of oscillation very small, because it executes small oscillation. When execute small oscillation, you can set any formula for it. When an object oscillates, for that we have to know equilibrium points. Okay, stable and unstable equilibrium. What do you mean by equilibrium? Okay, what is equilibrium? Equilibrium means system is at rest and mathematically no net force acting on the system. So net force acting on the system is zero. So we call a stable equilibrium when if you slightly disturb from its equilibrium position, then it executes simple harmonic motion, and after some time it will again come back to its original position. But unstable equilibrium means if you slightly disturb it, we we cannot get its original position from that. Okay, because it may not execute any motion. Uh, for example, suppose we are putting a stone on a top of a mountain. When you slightly disturb it, it fell down. Okay, so it is a case of unstable equilibrium. Suppose we are putting a egg on a table and just put like this. It is in equilibrium. If you slightly disturb it, it fell down and also broken down. We cannot get its original position. On the other hand, just like a simple pendulum case is something, is a simple pendulum. If you slightly disturb it, then it execute simple harmonic motion and finally it come back to its original position. That case is known stable equilibrium. How you know it? For stable equilibrium case, potential at equilibrium point is minimum. For unstable equilibrium case, potential at the equilibrium point is maximum. And you know how you mathematically check a maximum and minimum quantity. Okay? Hello? Hello?
Yes, sir.
Okay. So stable equilibrium means if a small disturbance of the system from equilibrium results in a small bounded motion. Unstable means if an infinite disturbance produces unbounded motion. For example, pendulum at rest, stable equilibrium, egg standing on one end, unstable equilibrium. So potential energy is minimum for the stable equilibrium and potential energy is maximum for unstable equilibrium. In potential energy V, equilibrium means force is zero. Force is negative gradient of potential. So negative of dv by dx 0 means dv by dx is equal to 0. So we are considering equilibrium point means we are considering dv by dx is equal to 0. So first we check equilibrium point or not. How? If you found dv by dx potential is given. If you found dv by dx is 0, then it is equilibrium point. Then we go for second derivative. If del square v by del x square is greater than 0, then it is stable equilibrium. If del square v by del x square less than 0, then it is unstable equilibrium. Okay. So for getting equilibrium point, we have to set dv by dx is equal to 0. Now formulation of our small oscillation problem. For a conservative system, we consider here for simplicity, we know let's say V is a function of position coordinate only, then force or generalized force is negative gradient of potential. 0 means equilibrium position. 0 refers to equilibrium points, and equilibrium point force is 0. So del V by del Qi is equal to 0. Let's say we can consider points Q01, Q02. It is the extremum of equilibrium configuration. Suppose a system has many points. For first point, when it is equilibrium, coordinate is Q01. Second point Q02. Third point Q03. A system with a number of particles, okay, for each particle. Let us consider the stable equilibrium. Here the departure from equilibrium position very small. So only for stable equilibrium it executes simple harmonic motion or small oscillation. We don't discuss unstable equilibrium because unbounded motion there is no oscillation. Okay. When it asks to find the frequency of oscillation, we only focus for stable equilibrium. We have to first calculate equilibrium point, then check it is stable or not. Then only we go for its frequency. If it is unstable, then there is no frequency, no oscillation. So it is the formulation of the problem, how this problem small oscillation set. Uh, okay, it is not so important, but problems are very important. For setting this problem, let's say our equilibrium point is Q01, Q02, Q03, and a small deviation from it, when it is slightly disturbed, it executes simple harmonic motion. That deviation will be from equilibrium position denoted by eta. I means for first particle Q1 is equal to Q01 plus eta 1. Second particle Q2 is equal to Q02 plus eta 2. This is equilibrium value, this is deviation. Because our motion is derived only variable eta 1 because this is a constant. So now eta I are considered generalized coordinate. Our problem reduced to eta I. So again expanding potential energy in terms of Taylor series, potential and any potential energy can be expanded around the potential energy equilibrium point. This plus del V by del Q eta I, then del square V by del Q del Q Taylor series expansion. No? Okay. I also neglect the higher terms, but if here equilibrium position, this quantity is 0, del V by del Qi, the force is 0. So we have this term plus this term, neglect the higher terms. We have a just quadratic term. You see half del square by del I is into eta j. Is parameter, so x square time. It is quadratic term. So the first term RHS potential on the equilibrium, it is equilibrium potential. For stable equilibrium, minimum potential. Let's for simplicity set minimum potential is 0. It may be positive, but we can set it's 0. So we have only one term. So our final potential energy is this one. Half d square v by d square, which is commonly written as half ij v ij eta I eta j. V ij means del square v by del qi into del qj, which is calculated at equilibrium point. Okay. So if you check it change ji, so it is not affected. Vij same as Vji. Similarly, we know that kinetic energy is half m q dot square or qi kj in terms of ij. I can write ij m ij qi dot qj dot. Okay, comparing with this, I can also write half t ij eta I dot it, because in place of qi, I put q01 plus eta 1, q02 plus eta 2. So finally it convert to eta dot. So kinetic is nothing but half mij. I take mij or tij, so eta I dot eta j dot. So there is a final formula like this Lagrangian T minus V half ij tij eta I dot eta j dot minus Vij eta I eta j. It is from this Lagrangian we actually calculate the frequency of small oscillation. Clear? Hello?
Yes, sir.
With the formulation of problem, okay, actually in the examination problems are asked, but how I calculate it. So this is the Lagrangian. No? So using Lagrange's equation of motion, we know d by dt del L by del eta I dot minus del L by del eta 0. Putting this L here, we get this equation. If putting derivative, then we found this equation. From this equation, we got a solution. This is actually see some x double dot plus something omega square x is 0. It is nothing but actually present a simple harmonic motion. Put solution, or you can say a second order differential equation by using auxiliary method. You can solve it and found let's root will be Ca e to the 1 minus I omega t. That's like simple harmonic motion. It's the same equation. X double dot or y double dot plus omega square y is equal to 0. Putting this root, we found Vij minus a square omega square Eij is equal to 0. And this 0 means since it is, all j's are unknown, we set Vij minus omega square Tij mod is 0. That is V minus omega square t mod should be 0. It is the condition. V minus omega square t means V11 minus omega square t1, V12 omega square t2 are 0. This is the required condition where omega represent the frequency of oscillation. Okay. Come to one-dimensional problem. It is general asked. For one-dimensional problem, we have no kinetic energy is equal to half mx dot square. For harmonic oscillator, its potential energy is equal to half kx square. So here this equation represents one dimension, so no component, only V minus omega square t is 0. So in place of this V, which actually Vij, that is the coefficient with half Vij xi xj, that is k. For one dimensional problem, V is equal to k, similarly t is equal to m. So V minus omega square t determines 0 means k minus omega square is 0, omega is equal to k by m root 2 over. But Vij, what we take k, this is basically equal to del square V by this quantity, del qi del qj. Or if one dimension, we write qi qj same del square V by del x square. So omega is k by m root over means in place of k putting this, we found del square V by del x square at x is equal to 0 by m root over. This is very important formula. By using this formula, you can calculate frequency of oscillation for any system obeying small oscillation. Okay, this is the potential is given. From that, you can calculate del square V by del x square and dividing m and take root 2 over, you find the frequency. Okay. This type of question also asked in your examination. A problem is given, find the frequency. Problem means potential is given. Hello, any problem? Hello?
Sir, can you please solve any example?
Okay, we'll do some problems. So, okay, maybe this I'm not going to this actually calculate to the states. When each frequency corresponds to one kind of oscillation. So these frequencies are known as normal frequencies. For each frequency, one kind of motion. If there are 5 frequencies, then there are 5 type of motions. This is known as normal frequency, and for each frequency we have coordinate known as normal coordinate. Okay, we can find different from this expression. Actually, this is a one dimension reaction problem. For general problem, this is a general expression. If it is a n cross matrix, then we have n roots. If it is a 3 cross 3 matrix, then we have 3 value of omega. Okay. So there are 3 normal modes. Each value of omega correspond to one mode of oscillation known as normal mode, and 2 normal mode are completely independent. We can make this fact explicitly by introducing a new set of independent coordinate. Each mode have one coordinate that is called normal coordinate. Okay. If there are so many oscillations, then there are so many normal coordinates. Suppose omega 1, for omega 1 frequency oscillation, zeta 1 is the coordinate, omega 2 zeta 2. Okay. By setting this, there is a slight simple calculations. If you do this, you can convert our coordinate from eta to zeta, and they should obey these equations. Okay. If that is come to a problem, actually in a problem, if we take t expression like this, from our ij, ti, eta z, and Tij is the same as Tji. Similarly, Vij expression this, Vj is Vji. It is one example of triatomic molecule. Suppose 3 molecules like this figure. Let's say water molecule H2O, 2 hydrogen, 1 oxygen, small m plus hydrogen, 1 is oxygen. They have this type of, if this is linear, then this type of configuration. What is the potential energy here? It is just like a simple harmonic oscillator. We have half kx square. So what is the distance between this? X2 minus X1, and if you consider from equilibrium position B, then X2 minus X1 minus B. X2 minus X1 does change. When its equilibrium distance is B, if you slight disturb it, then they will change. So the distance will be X2 minus X1 minus B. If you can neglect B, then no problem. Final, because B is a constant, its derivative has no meaning. Then second thing, here the distance, equilibrium distance is B. If you slightly disturb it, then the net change will be X3 minus X2 minus B. So total potential of the system half kx square looking like this. Is not it? Hello?
Yes, sir.
Half kx square. Okay.
It is minus half kx square. Or
No,
plus
only
half-
potential means half kx square, not minus. Plus half kx square. Force is negative minus kx. If you take derivative negative gradient of potential, force is equal to minus kx. Wait a minute. But if you take it derivative, sorry, force is minus kx. But potential, when you calculate, force is negative gradient of potential. So you integrate with a negative sign. Our force is minus del v by del x. So v is equal to minus integration of f dx. Minus minus plus. So kx dx integration is kx square by 2. Clear?
Yes, sir.
Okay. So using our coordinate eta, if you set eta is equilibrium position minus exact position difference xi minus x0, so it observe eta 2 minus eta 1 square, eta 3 minus. Or you can start from this. Actually, it is showing analysis. We know if the two particle distance eta 2, eta 1, eta 3, eta 2, eta 1, eta 2, eta 3, the potential energy is this. If you open the square, it will like this. Is not it? I can like it in a matrix form for a tensor, V tensor. Vij, actual tensor matrix form means eta 1 square means eta 1, eta 1. 1 component. Okay, here 1 2 component means eta 1 into eta 2. But eta 1 eta 2 have minus 2 into eta 1 eta 2. But it is symmetric, it is same as eta 2 eta 1. So I assume that the eta 1 plus eta 2 plus eta 1 into eta 2 plus eta 2 eta 1 is equal to this. So this, instead of this writing minus 2 for this component, I divided into both 1 2 and 2 1 component. Clear? From this expression, when I write the matrix, I see eta 1 square means eta 1, it is 1 1 component. Eta 2 it is 2 2 component. Okay, okay. Eta 3 it is 3 3 component. When 1 2 component is same as 2 1 component with symmetric matrix. But here only written minus 2 eta 1 eta 2. So I have to divide between, since these two components are same, but eta 2 eta 1 is not here. So I have to divide it into 2. That I write it is minus eta 1 eta 2 minus eta 2 eta 1. A B B A same. So I write here minus 1 only. Similarly here eta 2 eta 3 means I divide eta 2 eta 3 minus eta 2 eta 3 minus eta 3 eta 2. So I take minus eta 2 eta 3 minus k. Here minus k. Half. How you get the component? Half Vij, it is Vij into eta square. Eta square half cancel, only this is our component for each one case. Since 1 3 is 0, does not appear here, that means coefficient is 0. So it is 0. Are you getting my point? Hello?
Yes, sir.
Okay. So, okay. Again, kinetic energy for this system, half m x dot square, but there are two small masses, one capital mass. So half n x dot square, half n x3 dot square, capital M x2 dot square. Or you convert to eta 1 dot square, eta 3 dot, eta 2 square. From here, how you get the component? here only component of eta 1 dot eta 1 dot. So component is m. So half Tij eta dot square Tij, this is matrix. But there is no product term. So all product term will be 0. Only same term, eta 2 term, capital M, eta 3 dot small m. Okay. So then we count v minus omega square t is equal to 0. This is the expression. And we put the we have a v matrix, we have the t matrix, one difference v minus omega square t 0, and this root will give you different value of omega. Solving this, you get these are the 3 roots for omega. So there are 3 frequencies. Okay. Now come to our one dimensional problem. A potential is given Vx is equal to ax square plus v by x square. Find the angular frequency of small oscillation about minimum of the potential. So how you solve it? First to get its equilibrium point. Equilibrium point means for equilibrium point f is equal to 0. F is equal means minus del b by del x 0. If minus is 0, then obviously that number is equal to 0. Del b by del x is equal to 0. So now take its derivative. What will be the result? If you take derivative, if this b, then del b by del x will how much? Tell me. If take a derivative 2ax minus, hello? What is the derivative of b by x square? X to the power minus 2. No? So minus 2 b by x cube is equal to 0, equilibrium point. So what is the value of x? Actually, take it to one side, so it will become this. So 2 cancel. So what you get? X cube. So x cube x is equal to x4 is equal to b by a. Isn't that it? So you found x4 is equal to b by a is the equilibrium point. So that it's if take a root over, that is solution will be x square is equal to root over of b by a. X square is equal to root over of b by a. Hello? This is the equilibrium point. Then take its second derivative and put this value. Whether it is small oscillation or not. Actually, this is only since 1 point. If you put this, okay. So second derivative will how much? First derivative this 2ax. Its derivative second derivative means 2ax derivative is 2a minus 2b s cube derivative is 6 and 3 by x4. 6b by x4. Put x square and b by a. So x4 is equal to b by root over. So x4 is equal to b by a. Putting this, you check. What is the value? It is 2a minus 6 B divided by B by A. Oh, sorry, it is plus. When you take derivative, it is already minus. So minus 3. Minus 3 means minus 2 minus 3 plus. It is plus sign. So it is equal to, it is second derivative del square V by del x square. Actually, here we calculate del square V by del x square. This is equal to this plus plus, so finally it is equal to 8a. 8a is greater than 0 or less than 0. Given a, b are positive constants. So result is 8a. 8a is, hello? A greater than 0. So 8a greater than 0. So del square b by del x square greater than 0 means b is maximum or minimum? Second derivative greater than 0 means b is, hello, minimum. So it is stable equilibrium case. So what is the frequency? Formula is given. Unit mass given. So m is equal to 1. We have the formula del square v by del x square at x equilibrium, at equilibrium point. What we have already calculated by m root 2 over. But here m is by m root 2 over. But m unit mass means m is 1. So it is only root 2 over of del square v by del x square. Del square v by del x square is equal to, we have found 8a. So frequency will be root 2 over of 8a. Okay? Clear? So a potential is given. What we do? First we take its derivative to get the equilibrium point. But del v by del x is equal to fx minus, but minus if multiply 0 then it will be same. So first check the equilibrium point. Del v by del x, setting del v by del x 0, we have found its equilibrium point. Then we calculate second derivative and evaluate at its equilibrium point. Check if it is greater than 0, then potentially minimum and it executes a polar motion. If less than 0, then our problem stops there. There is no oscillation. We have only calculate for stable equilibrium or for potential, minimum potential. Okay. So then using this formula, I found it. Okay. This type of problem asked. It is another problem. Please do it. Tell me the answer. Potential is given Vx x into x minus 2 whole square. So find the time period. This time period means 2 pi by omega. If I calculate omega, then time period. Tell me its equilibrium points. How you get equilibrium points? For equilibrium points, you have to set del v by del x is equal to 0. Tell the values of x for which del v by del x is equal to 0. Take it derivative, how much? X into x minus 2 whole square. If you take x minus 2 whole square means x square plus 4 minus 4x. This is our potential V. So calculate del V by del x. If multiply x cube, so that x cube means its derivative is 3x square plus 4x derivative is 4 minus 4x square derivative is 4 minus 4 into 2x 8x. Okay. this equal to 0. How you get the roots? You know the quadratic equation. X is equal to minus b plus minus b square by 2. For AC divided
Sir,
by
it is. Hello, sir. Sir, it is x is equal to 2. X is equal to 2 by 3.
oh, check it. X is equal to 2
X is equal to 2 by 3. Two roots.
two roots. So check its second derivative at which point we get a negative sign. Second derivative. Oh. At second derivative will be obviously 6x minus 8.
6 minus 8.
Okay. If put 2, then 12 minus 8 4 greater than 0. But if you put 2 by 3, 4 minus 8 less than 0. So x is equal to 2 by 3 is a stable equilibrium point. Isn't it?
Yes.
Hello?
Yes, sir. Yes, sir.
X is 2 by 3, we get 2, 3 minus 4. So what is the omega? So you have to according to formula, unit mass given. Unit mass is m1. So you have to only calculate root over of del square v del x square. Del square v by del x square. Oh, sorry. If x is equal to 2 by 3, then is minus. Minus means maximum. You know it? If del square v by del x square is less than 0, then maximum. For minima, it is greater than 0. For point 2, x is equal to 2, it will 12 greater than 0. So x is equal to 2 is the stable equilibrium point or minimum potential point. Is not it? Hello?
Yes, sir.
We need potential minimum. For potential minimum, second derivative greater than 0. So for this, we found not minus 4 is 6x minus this is plus 4. So omega will be root over of plus 4. Here also you can check because it should be a valid quantity. If it is negative, then imaginary, it is not possible. Okay. So omega is equal to how much? 2. So question is calculate time period. Time period t is equal to 2 pi by omega. So if you divide 2 pi by 2, the answer will be pi. Okay. Clear? This type of it is another problem, you have to do it. Okay, I'm not good there. There is also another problem. Okay. This is all about small oscillation. Another thing, one is I think Rutherford scattering we have. Scattering in a central force field. Scattering process. Okay. Scattering you can find in both classical and quantum mechanics, but the procedure is same. The problem of scattering, a uniform beam of particles incident on a target. Here in central force problem, we consider that uniform beam of particle incident on a central force. Means what here? Let's say planets are revolving around the sun. If we consider it is a scattering process, actually sun is the target, planets are just like the beams. They are coming towards sun. Due to its attraction, they are revolving in the elliptical path. So consider uniform beam of particles incident on a center of force. All the particles of the beam have same mass and same energy. For simplicity, consider that. It is also applicable in for the motion of electrons around the nucleus or any other case scattering case, or alpha particle scattering case. Okay. So particles are either electrons, alpha particles, or planets. Target is nucleus or sun or gold foil. The force between the incident particle and the center of force falls of zero for very large distance. When distance is very large, then there is no force. Force is inversely proportional to r square, so it will be obviously zero. When particle approaches center of force, it will be either attracted or repelled. So it will deviate from its direction of motion, a straight line trajectory. After passing through the center of force, the particle goes away and the force acting on the particle will eventually diminish once again approaches the straight line path. In general, the final direction of motion is not the same as the incident direction, so we call it scattered. Suppose a particle is coming like this, there is a center of force, it will affected by it, so it will either attracted or repelled. If attracted, it move like this. If repelled, it move like this. So this process is called scattering. Incident direction is not same as final direction. There are some terms associated with scattering. One is in intensity of flux density, uh, number of beam coming per unit area, per unit time. Scattering angle, angle between incident beam and scattered beam. Impact parameter. Actually, if we draw a perpendicular on the direction of the incident beam from the scattering center, suppose this is your scattering center or so on, whatever. If planet is moving like this, then if you plot this distance, the center of scattering point, perpendicular distance, this is the center of scattering point, let's say, and this distance is known as impact parameter. Perpendicular distance between the direction of beam and the center of the uh, target. And scattering cross section, which we have to calculate. Cross section means when we consider a uniform beam of particle moving with flux density I0 toward the scattering center, then the area perpendicular to the path of the beam, so the where particle hit area is scattered is solid angle d omega. Scattering cross section basically an area, and we consider the number of particle or scattered particle collected through that area. It's considered a specific area around the center of force or target where the number of particles are collected. The number of particles scattered from the area per unit time will be I0 d sigma. Okay. We can see it. Yeah, okay. The figure I see. This actually figure. Suppose incident beam are coming here, and okay, there is a center of force here, or here you can say. So the particles are affected by this. This distance is your impact parameter in direction of beam, and distance is the center of force. Okay, and they cross through a particular area. We have collected a scattering area, d sigma, a scattering cross section. We are considering the particles which are scattered through this region only. As an area, we study the particles which are passing through this area only. If it is passing through this, we are not considering that for the T sigma case. Okay. There is actually basic formula. Uh, these are terms. Again, scattering cross section. From this analysis, it is simple calculation. You have to get a formula for this. This is the scattering cross section formula. S we already know impact parameter. Sigma theta, if it is scattered through an angle theta, then cross section is equal to sigma theta minus S by sine theta ds by d theta. Actually, we use this formula for getting the Rutherford scattering, which is asked in our examination. Find the scattering cross section for Rutherford scattering. Okay, we have to calculate this. and Rutherford scattering cross section. You check this formula. For Rutherford scattering means a positive charge particle mass m is scattered by a heavy nucleus. Okay, there is a heavy nucleus. Central nucleus, and some positive charge particle is coming towards here and is scattered with this. The other pole scattering actually, if you take its charge is ZE, it is Z prime E, then what is the Coulombic force between them? Formula 1 by 4 pi epsilon 0 Z Z prime E by R square. Okay. From comparing this, we found K is equal to this minus this K by S square if central force Z Z prime E square by 4 pi epsilon 0. But we know that 1 by R is equal to C into 1 plus epsilon cos theta theta prime, so set theta prime 0, 1 plus epsilon cos theta, and eccentricity is equal to 1 plus 2 is A square by MK square. So put all this, we found eccentricity formula is this. K value is given, putting but angular momentum related with impact parameter J is equal to S into 2me root 2 over. J is equal to S into 2me root 2 over. So in place of J, putting this, we found this expression, eccentricity is this 1 plus 2e s 4 pi epsilon z by square. 1 plus x square means it is square term is always positive, 1 plus something. So root over is must be greater than 1. And 1 by r is equal to c plus 1 plus epsilon cos theta. Putting the value of all things epsilon this 1 and okay 1 plus epsilon root over cos theta 1 plus this, and the quantity c we already get from comparing this. C is equal to this one written here. Putting this, we found this formula 1 by r is this. We have to one condition scattering. When it is scattered, actually, you see the object is making an angle theta. What is the relation between this incident angle theta and scattered angle? It is actually capital theta, small theta and capital theta. It is incident beam direction. Angle theta coming like this or here and going like this theta. But if you see this, let's say it is a symmetric. The axis is symmetric and we make a line between them, then this angle will be same alpha plus alpha. 2 alpha plus capital theta is equal to 180 degree. You know it? 2 alpha plus capital theta is equal to 180 degree. Okay, but if r is very large, then theta and alpha actually matches. So we put theta is equal to alpha. That is the condition. Capital theta is equal to pi minus pi is 180 degree, 2 alpha. So alpha is equal to pi by 2 minus theta by 2. For r infinity very large, theta is equal to alpha. That means here is small theta. The small theta is equal to pi by 2 minus capital theta by 2. Okay. Theta, small theta, which is equal to, okay. Putting this theta and alpha equal to alpha, we find 1 plus epsilon cos alpha is equal to 0, cos pi by 2 minus 1 by e. E is already given here. Okay. So putting this and simplifying, we find the expression for S. S is proportional to cot theta by 2. Then using the formula, we can calculate cross section ds by d theta, ds by sin theta. We found finally sigma cross section proportional to sin per theta by 2. This scattering of all mathematical details given here. You can okay. Okay, this is the final expression. But generally in your question problem type questions are comes, they are not asking any derivations. So you only know the derivation. If problem will ask, then you solve it. Okay? Hello?
Yes, sir.
Okay. So on MPH-2 is I think over. I discuss all the things. In the next class, we discuss about MPH-6. Okay. Can I take a class tomorrow?
Sir, timing?
5 p.m.
Okay, 5 p.m. Okay, okay.
Tomorrow, I think there is no class
No,
tomorrow.
sir. There is a class from Ganeshwar sir 5 to 6.
So I will take 4 to 5.
Yes, sir. That will be fine.
Okay, I will take 4 to 5. Okay. Because
Okay.
I think I cannot take class on Monday and Tuesday. Instead, I will take on Thursday. Sorry, Thursday, Friday. I'll tell that. Because I have two classes on Monday and Tuesday, 21 and 22. I have a meeting on that day. So I may not take on Monday or Tuesday. I'll take, I think, one class on Friday. Today I take one class, tomorrow I will take one class, then next Friday we will take another class. Okay?
Okay, sir.
Okay. Thank you. So next class we will discuss about MPH-6. MPH-2 is I think over. If any doubt you can ask anytime, okay? Or like, write the question in that group, or you can all person to my personal WhatsApp. Okay? Okay. I am leaving.
Sir, can you send these notes in?
Yes, yes, yes. I am.
Okay. Thank you.